Hello, welcome back to the course on Polymeric Biomaterials. We are now starting off on a new theme, namely bulk behavior and responses. Now, so far in the course, we have looked at a few different themes. After covering the introductory concepts, we started looking at structure property relationships in polymeric biomaterials. And after that, we looked at temperature and solvent effects. And then following that, we looked at a series of different types of synthetic and natural polymers, structure property relationships as part of those polymers and how that impacts function and performance. Now, from this week onwards, for the next several lectures, we will be turning our attention to bulk behavior and responses, and as part of the first lecture under this theme, in today's lecture, we will be focusing on mechanical properties and responses, and this is the first lecture of a two-part lecture on mechanical properties and responses. So, in today's lecture, we will be first looking at some introductory remarks about bulk and surface properties, and as part of that, we will also contextualize the importance of mechanical properties. Then we will take a quick look at the different testing modes that are available to us as part of testing polymeric biomaterials for different applications. And then we will focus quite a bit on the engineering aspects of mechanical testing, namely looking at how stress strain curves are generated, how do we understand elastic deformation and plastic deformation, how do elastomers, for example, deform, how do thermosets deform, how do thermoplastics respond to load. All these questions we will try and answer. We will also look at molecular mechanisms. Essentially, when you test a material mechanically in some form or fashion, you are measuring bulk properties, but you can relate that to specific changes that occurs in the microstructure of the material. And as part of molecular mechanisms, we will try and map out some of those changes to the microstructural changes that occur at a much smaller length scale. And then at the end, we will look at some properties, mechanical properties of polymeric biomaterials for some specific polymers that we have already looked at in this course in some detail. First, look at surface versus bulk properties. Now, when we talk about surface versus bulk, it sort of sets up an expectation in some sense that you're going to get very different properties depending on what you're looking at, right? And as it turns out, both those properties are extremely important for the function and performance of polymeric biomaterials. So, it's not like one is better or worse than the other. Both of them have to be equally looked at. Depending on the application, you might end up prioritizing one over the other, but nevertheless, for eventual implantation, function and performance, both of those are very critical. Now, why are they critical? First thing to note is surface properties determine cell material interactions and what you would first think of as the initial aspects of biocompatibility. Because when you implant a material, the serum proteins in the blood will first adsorb on the material, and because we are using the word adsorb, it should be clear to you that this is a surface phenomenon. And therein surface properties such as charge, roughness, wettability will play a very important role in determining what kinds of proteins adsorb on a surface, and also determining thereafter how cells come and attach to the surface and how the biological microenvironment decides to deal with the material itself. And this is something that we will focus on later in the course, namely surface properties. But you notice that for the long-term performance of the biomaterial itself, bulk properties are important, because in that term biocompatibility itself is embedded the idea that you are looking at an appropriate host response in a specific application, right. So, you are designing materials for specific devices or materials for specific applications, and it is critical that the bulk properties are correctly designed to have the appropriate kind of responses and for the implant to perform well in your specific application. Examples of that include maintaining the correct physical shape over time or deforming as required For example, stimuli responsive polymers will undergo large changes in macroscopic structures, and that could be by design, right. So, all that has to do with bulk properties. Then carrying mechanical loads. Many of the polymeric biomaterials that we have looked at are integrated as part of devices to perform specific mechanical functions. So, there it is important that mechanical properties are contextualized. And one thing to keep in mind is the role of processing here. So, one thing that we have seen earlier is this idea of structure affecting properties, affecting function and performance. Now, function and performance has to be contextualized to a specific application. But what is not said here explicitly and what should be quite clear to you by now is the role of processing. Because the structure property relationships, many of them that we have looked at, are also deeply impacted by how the materials are processed. And as part of the theme that we are currently looking at, which is bulk responses, we will deal with processing separately later in the course. But this is just to remind you that processing has a very important role in determining structure and properties. And when these polymers are processed as scaffolds, for example, such bulk properties would also include things like porosity, pore size, permeability, etc. So, these are all important aspects to keep in mind. Now, that being said, we will now turn our attention to mechanical properties particularly as one aspect of bulk properties and ask why are mechanical properties critical. First of all, we note that mechanical properties are application specific. So, the device or the material that you are preparing has to be contextualized for the application. And what is very important is any implant that you are planning to use has to be designed for and also tested in appropriate environments that approximate in vivo conditions. So, there is a specific site of implantation that you are thinking about, or a specific location within the host where the material is going to be deployed or the device is going to be deployed, and those locations are associated with specific microenvironmental conditions, what we are calling here in vivo conditions. So, those in vivo conditions must be accounted for or kept in mind when you are designing the material itself. So, all the testing that has to be done in vitro, a lot of it has to account for eventually what kind of microenvironments the material will be subjected to. You can also think about it from a technology readiness level perspective, which is to ask at what stage is your product at to make the claim that it can now be deployed in the host. So, that is one very important aspect. Another important aspect to keep in mind when you look at mechanical properties is that many polymers that we use should be able to withstand different kinds of mechanical forces. For example, there could be heavy loads depending on where you are implanting it and what the application is. There could be repeated cyclic loading. If you are thinking about ligament replacement, for example, or ligament reconstruction, you are going to have back and forth cyclic loading, right. Is your material suitable for that application? Or if you are using, if you are making small diameter vascular grafts or vascular access grafts, can your material withstand pulsatile stresses because of the blood flow? So, all of these things have to be deeply looked at. Now, as we have already hinted at, polymer structure and architecture play a very important role in all this, which are affected by processing. Two other factors that we have already looked at under an entire theme, again you see that theme repeats, the role of temperature and solvents. So, that is why we looked at the role of temperature and solvents earlier on in the course. So, when we now talk about what the role of temperature is, what the role of solvent is, it will be fairly straightforward for you to understand and follow the content. All of these affect the mechanical properties. Now, before we proceed further, just to pick your brain a bit, I would encourage you to pause now and reflect on 3 different polymers for 3 different applications. One is for ligament reconstruction, One is to be used as a vascular prosthesis, the other is a liner in knee prosthesis. Now, based on the concepts we have seen so far in structure property relations, temperature solvent effects, and under biomedical polymers, can you try and see if you can justify why PET, PTFE and ultra high molecular weight polyethylene, all of which we have looked at in detail, are used for these applications? So, why is PET one of the choices for ligament reconstruction? Why is PTFE one of the choices for vascular prosthesis? And why is ultra high molecular weight polyethylene the primary choice for, or cross-linked version of that is the primary choice for knee prosthesis? So, these are questions that you can ask. Now, you can answer these questions from multiple levels, but because we are looking at mechanical properties here, the perspective that I want you to think about is from a mechanical property bulk perspective. Of course, you can talk about surface properties of PTFE that make it suitable for vascular prosthesis, but what I want you to think about at this juncture is to think about the bulk and bulk properties. So, this is a good point to reflect upon and see if you can connect the structure property that leads to bulk properties for these polymers, resulting in their use for these specific applications. When we talk about mechanical properties, we are talking about mechanical testing and testing modes that give us specific properties. Now, the testing mode that you want to subject your material or device to is going to be determined by the forces that the material will be subject to eventually in vivo. So, the testing mode has to be appropriately chosen. Now, there is something called a universal testing apparatus. A picture of that is shown here, that is typically used for all the modes. The word universal simply indicates that it can be used for all forms of, at least the major forms of testing modes with the appropriate grips and fixtures. So, it can accommodate all of that. What are those modes? We will see in just a minute. What also you are doing here is to also account for controlled loading within a defined environment, where in the initial stages at least you are interested in primarily looking at controlled environments or defined environments, but also accounting for the fact that the material will be deployed in an environment where there is an aqueous buffer. So, that is the solvent, and that buffer is at 37 degrees Celsius, which is the body temperature. So, all our concepts earlier about that we have seen about temperature and solvent effects should be contextualized here. Now, there are standards available for testing modes and material types. Now, one important standard organization that sets standards is ASTM International. Now, ASTM cannot enforce standards. They put out standards, and there are agencies that can say, like the FDA, that can say, look, if you have made a material or a device and you have tested it according to ASTM standards, then there is already some standardization that is accounted for, as opposed to saying I have made a material or device and I have tested it based on parameters that I have chosen or modes that I have chosen that are not based on any standardized setup or framework. As opposed to that, if you say, look, my device or material has been tested in accordance with ASTM standards, then the FDA will take that perhaps more seriously. FDA will not demand or dictate or enforce that you follow ASTM or specific standards, but if you follow such standards, you have a higher chance of going through the approvals, because standardization, and that has to do with why standardization is important. The big name here is Charles Dudley. A very important pioneer in standardization in industries and in testing. So, why is this important? Because when you test materials under standardized conditions, it becomes easier to benchmark or compare. That is the reason why standardization is important, because if you want to claim that your material performs better than an existing gold standard, one way to benchmark that is to claim that you have tested your material under the same standardized conditions as the gold standard and claim that it performs better. right. So, that is some little caveats to keep in mind when you look at standardized modes of testing. And now would be a good time to maybe pause and look up some of these standards. I am just listing these out for you to get a sense of some ASTM standards for specifically for polymers and implants. So, some of these are specific to polymers and implants, different modes of testing, different types of applications, etc. So, I would encourage you to pause and look up some of these just to get a sense of what these standards look like, what is the context, etc. Now, we have looked at how the testing can be done using universal testing apparatus, and we have alluded to the idea of modes. So, now we will quickly look at the predominant modes of testing that are used for many of these materials. The first two are tension and compression, where axial load is applied, and if you pull this way, that is tension. If you push on both sides, it is compression, as the forces are shown here. Because remember, in all these types of testing, a load is applied and you are asking how does the material deform. So, this relationship between load and deformation or displacement is what you are interested in. The relationship between them is what you are interested in. You can also have shear, such as shown here. You can also have torsional mode of testing. You can also have bending, where the pair of moments are applied as shown here. These are largely the predominant modes. Of course, you will have many more modes depending on your specialized application, depending on what your property of interest is, what property is critical in that application. All of that will dictate what mode you use, but these are the predominant modes of testing. And even here, when we typically say mechanical testing, we generally refer to tensile testing, because it turns out that what you can learn from tensile testing, you can apply to those at least some of those concepts to other modes of testing as well. That's a good starting point at least. Now, there is one more important aspect to be noted here, because we are dealing with polymeric biomaterials. These polymers also can exhibit something called viscoelasticity. Now, this is a topic we will look at in a dedicated lecture slightly later, but this is something that you have to keep in mind, where now time becomes important, because there is a viscous component here. How the material responds is also a function of time, and some of that has to be accounted for even in tensile testing, because when you pull a material, how fast you pull will dictate what kind of properties you get. There are some minor details, subtle points to keep in mind as we go through this lecture. So, the first thing we will begin by saying is to make a distinction between mechanical properties and mechanical variables. Now, often these are conflated, and it is good to make that distinction right away. Mechanical properties are quantifiable values of a material under specific loading conditions. For example, what is the strain rate at a specific strain rate in the presence of phosphate buffered saline, for example, at 37 degrees Celsius. So, those would be conditions that you can specify, and what you extract from that test in terms of quantifiable values for the material would be mechanical properties. Examples of that would be measures of mechanical variables at which transitions occur, and what transitions are we will look at in just a bit, at which point it will become more clear. But that is a nice segue for us to look at what mechanical variables are. Now, these are not per se properties of the material, but are used in determining the properties eventually, and two very famous examples of that are stress and strain. Stress and strain, which you would be very familiar with from some basic course on mechanics, etc., or physics, would be not considered properties, but they are more mechanical variables. They can be considered properties only when the material transitions or when structural changes occur. Examples of that include yield strength, failure, etc. These are again things you might have heard of, which are ultimately obtained from a stress strain curve, but they represent important transition points. So that's one way to think about the relationship between mechanical variables and mechanical properties. You can also get properties from specific relationships between mechanical variables. So the relationship between stress and strain in some cases can give you something called a elastic modulus, as we will see in just a bit. So we made 2 points here. One is to make a distinction between mechanical variables and mechanical properties. Mechanical properties would include things like elastic modulus, yield strength, tensile strength, strain at failure. So all of these things are what you would think of as mechanical properties. Mechanical variables are not properties, but things like stress and strain can be in turn used to determine properties. The other point is you can find a relationship between them based on whether the material transitions or structural changes occur, or based on specific relationships under certain assumptions and constraints between the mechanical variables themselves. So now with that being said, we will now formally define stress and strain, because that's a good starting point for us. As we saw, you can go from mechanical variables to properties, right? So it's a good idea for us to first define what stress and strain are, and these are again things that you will be quite familiar with, but for completeness we are still defining them here. Stress is simply can be thought of as occurring from a load or a force that is applied to a material that leads to deformation. From a physics perspective, it is simply the force acting per unit area across a surface, and units will be in pascals, and stress is typically given as sigma is equal to force over area. Strain, which is the deformation or the response of the material to the applied load or stress, is deformation per unit length, and by definition it is dimensionless because it is the change in length over the initial length. So it has no units. Now one important aspect to keep in mind here is, let's assume you are doing tensile testing and you are pulling it this way. You are taking a material and you are pulling it this way. What area are you talking about here? Because the area continuously changes. As you pull the material, if I pull on this material is going to thin in the middle. So the area continuously changes, dimensions also, the length also continuously changes. So what area are you talking about here? Therein you will find one important distinction that is made in the literature, which is the difference between engineering versus true stress. And this is accounting for the fact that some of these features, or such as area and length, continuously change during testing. So engineering stress and strain would simply be based on the initial dimensions, and true stress and strain would be what you get at instantaneous time points as the dimensions change during the testing. And almost always what we are concerned about is engineering stress, because this is much harder to measure. We are almost always concerned about engineering stress. So that's an important distinction to make. So all we have said is, we have defined what stress and strain are. Stress is simply the force acting per unit area across a surface, and it can be thought of as the load or force applied to a material that results in deformation, and the deformation itself is quantified by the strain, or the extent of deformation is quantified by strain. Now, what is the relationship between stress and strain as part of a stress strain curve? Now, we will take the example of uniaxial tensile testing. When I say uniaxial, if I have a material like this, I am testing it only in one direction. I am not testing it in other directions, right? So just one direction, so uniaxial testing, that is common. And typically for these kinds of tests, you would have something called a dog bone geometry with round or rectangular cross section, like so. And why is this geometry preferred? There is a couple of different reasons. One is controlled failure location, uniform stress distribution, and allows reliable gripping. So, these two ends will be gripped in the clamps on the universal testing machine, and what you are testing really is this portion, and the gauge length is what actually matters. And this all one ensures uniform stress distribution and also ensures that in the interest of standardization you will have controlled failure. So, the material will not snap somewhere here or here, it will likely snap in the middle, and that is important. So, that is why the dog bone geometry is preferred quite often. And once you have made the geometry this way, the sample is tested under a constant strain rate. So, you are applying a constant strain rate. Now, you note that the word rate here indicates has a temporal connotation, right. Now, this is a very important thing to keep in mind. The strain rate, how fast or how slow you are pulling the material, will make a very large difference to the type of properties you will get from materials, especially polymers. And that is because I will give you a quick way to think about it, and we will do it more formally in a later lecture. You can think of broadly the strain rate as imposing one time scale in the problem, right. There is one time scale associated with the strain rate. Now, in polymer, when you look at different length scales, you can now think of multiple time scales in polymers for relaxation. You can think of time required for segmental mobility. You can think about the time scale associated with chains aligning when you are stretching. All of these things have to be contextualized against the strain rate or the time scale associated with how fast or slow you are stretching it, right. So, if you pull too fast, you may not give enough time for the chains to align. That may give you one set of properties. If you pull very slow at every stage, you are ensuring that the material can align itself, the chains can align itself, etc., then you may get a different set of properties. So, strain rate specification is very important in these kinds of testing methods. And in the test itself, the load cell and the extensiometer track the force versus displacement or load versus displacement, from which you can end up getting a stress strain curve that looks like this. And shown here are three different types of stress strain curves that you might possibly get from polymers. Now, this is a very famous picture. You will see this in almost any textbook that you will that you can look up, and the behavior is classified based on the qualitative nature of the stress strain curve that we get across brittle, ductile, and elastomer like. Now, brittle materials are materials or polymers that undergo failure without significant deformation. So, you see the point shown in the X here represents the failure point. So, these brittle materials fail very quickly without much deformation. These are typically associated with glassy amorphous polymers. You can have semicrystalline polymers also in some cases. You can also have thermosets that undergo this kind of a behavior, essentially very high slope in the stress strain curve and also failing quickly without significant deformation. And one example of that is polymethyl methacrylate, which we have seen earlier, which is typically used for hard contact lenses or bone cement. These materials, brittle materials, will also undergo catastrophic failure. They will crack, and the crack will quickly propagate, leading to failure. Now, compare that or contrast that with ductile materials that undergo what you would call plastic deformation, as shown here. Now, a lot of the materials that are commonly used are called plastics. Many polymers are called plastics, and that's because many of them will actually display some kind of behavior as shown in the ductile curve here. So that's one reason why the word plastic is synonymously used with polymers, although that's not entirely right. In common parlance, that's commonly used, and this is the reason why the word plastics, when we use them for polymers, we're actually talking about something specific. Now, these ductile materials undergo plastic deformation or yield, and what these are we will see in more detail in just a bit in this lecture. But we note here that they don't just fail. The stress strain, right away you see that the stress strain relationship is not linear, right? It seems to be linear till a certain point, and then it becomes non-linear, and then you see some onset of permanent deformation, etc. here, right? So all of these things make the material ductile, and the material will yield before failure, right? One good example of that is polycaprolacto, which will show this kind of a behavior. A third variety that we are showing here is that of an elastomer, where you can get very large recoverable strains. So this is typically what you would find with rubber bands, for example, and very large recoverable deformations, and you have to pull them to extremely large deform them significantly, sometimes up to 800,000% before they can fail. Now, examples of that include thermoplastic polyurethane, which we have seen earlier. Now, recall that thermoplastic polyurethane is unique because it has the processability of thermoplastics and the elastomer-like behavior coming from the soft segments in the polyurethane, right? So, it's a combination of the hard and soft segments that contribute to the properties of the polyurethane, right? A natural polymer example that we have seen earlier, elastin, which is a natural elastomer, right? So, those kinds of materials are elastomer-like. So, again, just to summarize this picture here, we are broadly thinking about now stress strain relationships based on the nature of the curves and classifying these materials as brittle or ductile or elastomer-like. Of course, you can have things in between as well, with some amount of one, some amount of the other, etc. But these are more classical textbook case examples. Now, with that stage being set, we are now in a good position to now start thinking about how to extract useful mechanical properties from these mechanical variables, namely stress and strain. And the first thing we will look at is the elastic deformation, and we are interested in specific mechanical properties, right? Now, first thing to think about is what do we mean by elastic deformation, right? Shown here is that first region, the initial region of the stress strain curve. So, if you just zoom in to this region alone, which is what we would call the elastic region, in the initial low deformation portion of the stress strain curve. So, we are showing that as a magnified case here, and again plotting stress versus strain, and what you are looking at is that region, because that is where you get reversible loading and unloading. So, this is the elastic regime where stress is only a function of strain at that point in time. In other words, the history of the material does not matter. How you got to that point, where it was in previously, are you going up or coming down, all of this does not matter, because the contention is if you know the stress, you get the strain if you are in that regime, or vice versa, right? And for purely elastic materials, these deformations will instantaneously go to 0 after the load is removed. So, if I am loading the material this way or this way, and if I let go, the deformations will immediately go back to 0. What that also means is there is no net or no permanent deformation. And the word instantaneously is put within quotes because, like I said, this is true only for purely elastic materials, and we are dealing with polymers here which are viscoelastic. So, for polymers there are other specialized types of properties that become important, namely creep and stress relaxation, which we will look at in more detail under viscoelastic responses. But this is again an important point to keep in mind, that this is true only for purely elastic systems where the deformations instantaneously go to 0 after the load is removed. And of course, the original shape, the ability to recover shape, right. Ability to recover the shape occurs along the same path. So, if I load the material this way, if I let go, it is going to come back exactly the same way. Load the material this way, it is going to come back this way. So, if again shown are two different curves for two different materials, let us say, it is going to come back along the same path without hysteresis. That should be connected to no net or no permanent deformation. And this elasticity has to do with a measure of ability of the material to store energy. And that is one way to think about the elastic deformation. Now, when you hear the word elastic, typically you think of something that goes up straight and comes back straight. So, you think of linear responses alone. Now, while that is quite often seen, that is not the only type of response that you can get in the elastic regime. You can also have non-linear elastic responses, such as what we saw with elastomers. You can have very large recoverable strains, but the response itself need not be linear. You see this curve here. If I keep stretching, the response is not fully linear throughout. For very large particularly deformations, I see non-linearity. But then the contention is it can still go back to 0 once the load is removed, right. So, the point we are trying to make here is that elastic responses need not simply be linear, they can also be non-linear, and that point is reiterated here. You can have linear and non-linear elasticity. Linear is typically seen for low deformations, where the load displacement is a straight line and it follows Hooke's law. And Hooke's law is useful because we can use that to come up with some properties for the material itself. For very large deformations, you can come up with, you will see actually non-linear responses, where the load displacement plot will be curved or non-linear, and you will have to resort to strain tensors, and a simple Hooke's law will no longer be valid in those regimes. One way to think about the relationship between linear and non-linear is to think of it as a relationship between load and displacement. And what we are trying to say here is the elasticity could be linear or non-linear depending on the type of material, depending on how far you have pulled it, etc. So, that is an important point to keep in mind. All we are trying to say is elastic need not always be only a straight line. So, two important properties that you can gather from such an experiment in the elastic regime are modulus of elasticity, which is simply given as the slope of this stress strain curve in the elastic region, where again stress is proportional to strain, and the proportionality constant is the elastic modulus or modulus of elasticity, which is a very important property, mechanical property for polymeric biomaterials. There is another property that you can extract from a stress strain curve in the elastic region, which is called resilience. It simply has to do with the elastic energy absorbed before returning to the native state. And to understand that, we have to first look at area under the curve, because this has to do with area under the curve. So, we will come back to this once we have looked at what area under the curve is. So, now again we are looking at stress strain relationships, and we have defined 2 points here in the stress strain curve. We are still in the elastic region, but we have defined 2 points. One is the point P, which is called the proportional limit. It is the point beyond which the linear stress strain behavior ends. So, this is an example where you see that beyond this point the stress strain behavior being linear ends. After that, it starts to become non-linear. This part is still the elastic regime, which means you go to that part, you can still recover your original shape, except the relationship between stress and strain is not linear. And then there is another transition point shown by Y here, which is yield, which is the start or the onset of permanent plastic deformation, beyond which the strains are not recoverable fully. So, if you go beyond point Y, you will see that you cannot, you have entered the next regime, which is the plastic regime, at which point you make permanent changes to the structure, the microstructure, thus being unable to recover the original shape once you have removed the load. Elasticity is the ability to reversibly deform without permanent changes, that is before point Y. So, this entire part you can recover because it is elastic. If you have gone beyond this point, you have entered the plastic regime. Now, coming back to resilience, it turns out that the area under the curve as shown here represents the elastic energy absorbed before the material can return to its native state, and it is simply the area under the curve from strain 0 to strain represented at this point Y, which is epsilon sub Y. Now, the word resilience, in common parlance also we use the word resilience to talk about people bouncing back from disappointments or hardships. That is one way to think about, it is a good starting point for us to think about what resilience means for these kinds of materials. The ability to quote unquote bounce back, and it is a representation or a measure of the ability to store energy. So, this has to be connected to resilience. So, that is what we are saying here. So, we have looked at 2-3 important ideas. One is the ability to extract modulus of elasticity from the stress strain curve, the ability to extract resilience from the stress strain curve, and both of these are associated with the elastic deformation. We have also defined 2 important transition points. One is a proportional limit, and the other is yield. Proportional limit is simply the point beyond which the stress strain relationship is no longer linear, but is still in the elastic regime, and yield is the onset of permanent deformation, and if you cross that, you have made permanent changes to the material, which means if you remove the load, the material will not return to its original shape. And yield can be thought of as ability for the material to dissipate energy, as opposed to ability to store energy in the elastic regime. And of course, resilience, properties like resilience are important for tissues such as tendons and ligaments. Or materials that are intended to replace them. Now, having looked at what happens in the bulk, we are now going to try and connect this to what happens in the microstructure. So, we are going to look at very briefly the molecular basis of elastic deformation. We are going to look at a qualitative picture of this. And we have at least 2 versions. So, you can take glassy amorphous polymers or semi-crystalline polymers as one example, where in the elastic regime, for many of these brittle and ductile polymers, you have secondary forces that stabilize the structure, right. So, as you are pulling the material mechanically, these strong secondary interactions between these chains resist the deformation, and shown here is an example of a semi-crystalline polymer. So, these represent the lamellae and these represent the tie molecules. Again, these are all concepts that we have seen in fairly great detail as part of lectures 12 and 13, crystallinity and amorphous nature of polymers. So, these pictures should not be new to us. What we are showing here is for very low deformations, like we said, the polymer stores energy, and that is the elastic regime that we just talked about. But when you test a when you mechanically test a semi-crystalline polymer like this, for low deformations, primarily what you are doing here is you are largely affecting the amorphous tie molecules. So, the amorphous regions reversibly align in response to an applied load, and because they are anyway amorphous, once the load is removed, the material goes back to its original position. So, in this case the material can fully go back in the unloading cycle to the original shape, because you have not made any permanent changes to the network, namely the crystalline aspects of the material are still intact, and largely what you are trying to break are secondary forces and secondary interactions which can be easily reformed. So, that is one way to think about glassy or semi-crystalline polymers, the microstructure of those polymers when you mechanically test them under tensile loading. Now, what is the case for elastomers, right, which is the other type of stress strain curve that we have looked at. Now, remember from our earlier discussions, we have seen that elastomers are lightly cross-linked networks, and we have already seen the examples of thermoplastic polyurethane and elastin. Now, note that because they are elastomers, they are unlike the glassy amorphous polymers which are more brittle or ductile. These would be rubber-like, meaning that they are already above their Tg, which means they are going to have very high segmental mobility, and any deformations will lead to a stretched state like so. So, you go from an unstretched or relaxed state to a stretched state, and then you can fully recover it. So, the arrow goes both ways, right. So, you can have, like we just saw, very large non-linear elastic deformation. So, the deformation is still elastic, which means the material stores energy, it can come back to its original shape without any permanent hysteresis, without any permanent damage to the structure, and the fact that it is simply non-linear, because you can go to very large deformations, 500, 600, 700% deformations, 5 times, 6 times, right, you are stretching it before it snaps back. That is why it is non-linear, especially in the large deformation regimes. Now, because one unique aspect about these materials we have seen earlier is the crosslinks, covalent crosslinks that stabilize the chains, these lightly covalent structures. So, there is no slippage across the chains because of crosslinks, and once you have stretched them out completely, it is the unfavorable entropy in that state that drives the material back to its pre-stressed coil state. So, essentially you have more conformational arrangements in the relaxed state compared to the fully stretched state. So, entropically it is unfavorable for it to remain there, so it will go back to its original position. And now would be a good time for you to recall our discussion about elastin in lecture 19, where we have looked at structure property relationships. We have actually seen what leads to these crosslinks, how are they cross-linked, and now we are connecting that structure property relations to mechanical behavior or bulk mechanical behavior. So, that is the connection we are making here. So, that is the elastic response. Now, we will move on to the plastic response or plastic materials. Now, here also again our interest is specific properties that we want to extract from stress strain curves, and you can define a series of properties in that regime, and polymers are quite varied and diverse, and shown here is simply an example of one version of a ductile material. Now, you can have many versions of this curve, there is not single version, but qualitatively they will largely look similar if you have a ductile material. Like we said earlier, the first word that should come to your mind when you think about plasticity or plastic is the ability for the material to yield, right. So, you can now define something called a yield point as we have seen earlier. So, P simply represents the proportional limit, Y represents the yield point beyond which you make permanent changes to the network. So, the stress corresponding to the yield point is called yield strength, at which noticeable plastic deformation occurs, and this is given in pascals. If you keep stretching it further till the point of failure, you can define a second property, namely the maximum stress before failure which is given by sigma sub Ts, sometimes called ultimate tensile strength. In this case, it happens right at failure. In some other cases, depending on the material, it can happen before as well. That is why the definition is important. The maximum stress on that curve that the material can withstand before it fails. Wherever that point is, that will become the tensile strength. And typically, you are talking of tens of, maybe hundreds of megapascals for this kind of a property. For modulus of elasticity, you can have even gigapascals, as we will see some examples towards the end of this lecture. You can have a third property called strain at break, which is simply the strain corresponding to when the material breaks or fails, which is simply given by epsilon sub break, beyond which the material, at which the material has just failed completely. And this could be as large as 1000% for elastomers. Ductility is another property which is the value of the plastic strain required to break the material, right? That is how ductility is defined. And toughness, again, these are words that we use quite loosely in common parlance, but you see they all have very specific engineering connotations. So, these words must be used carefully because each of them has a specific definition. Toughness can be thought of in some sense as being analogous to resilience, except here you are looking at the entire stress strain curve as shown here, right. So, the area under the curve represents the energy absorbed. For resilience, we said it is the area under the curve in the elastic regime, both linear and non-linear. Here we are saying it is the energy absorbed before the sample breaks, namely the entire stress strain curve. And if you now look at it for a ductile material, tough material, this is the area under the curve. Now, can you think of why this material is called ductile and tough and this material is called hard and brittle? It should be fairly clear looking at the shape and nature of the stress strain curves why this material is called ductile and tough. The area under the curve is very large, making it tough, and the fact that it is ductile is because it can undergo plastic deformation, and this being hard and brittle is because it has very large elastic modulus, but also fails quite catastrophically for not very high deformations even. And of course, the area under the curve for toughness is given by this equation. Now, there are some more aspects to look at when we think about the plastic deformation. Now, we have already looked at yield strength, we have looked at tensile strength, we have also looked at strain and break. Now, one important idea that happens to the we have to look at that happens to the material as you are stretching it in this regime, particularly in the beyond the yield point, is this idea called necking, which is shown here. So, you see the arrows indicate here the formation of a neck which grows with time as you keep stretching, and material is going to eventually fail somewhere here in the middle, right. Now, this necking, like I said, typically develops after the yield point, and the chains for this kind of a material, example of a material shown here in this stress strain curve, the chains initially lose their structural integrity and the elongation occurs by neck growth in this region. And this necking is going to result in an area reduction, but you see once you have gone to fairly high deformations, these chains start to reorient again and resist deformation. So, you get some kind of a strain hardening kind of behavior here. Why, etc., we will see when we look at molecular mechanisms in just a bit, but these are some important aspects to note, at least qualitatively, when you look at a picture like this. So, one way to maybe ask questions is when you look at a plot like this, a curve like this, you can take it piecemeal and ask what is happening to the material at different parts of the stress strain curve. So, if you ask questions like that, then you will dig deeper into mechanisms for why the shape of the curve is like this versus another shape, right? For example, why does this increase towards the end? All of these things can become clear only when you ask questions like that. So now, all we are saying for this picture here is saying that there is a mechanism by which a neck can form beyond the yield point, and as you keep pulling it more, the neck is going to grow, and as you keep deforming it more and more, you are going to have some strain hardening because of chain alignment, which is going to resist deformation, and eventually it is going to fail. Now, what is the molecular basis of deformation in semicrystalline polymers? So, what we are going to do here is, just as we saw for elastic regime, we are going to take a semicrystalline polymer and go from start to finish and try to see if we can map out, if you will, structurally what is happening to the different aspects of the material itself, or the polymer itself, in the different regions of the plot that we saw on the previous slide. So, first of all, we notice that because we are considering semicrystalline polymers, there is an interplay between the amorphous and the crystalline regions in response to an applied tensile force, right? That close interplay is what gives the curve its shape in the different regions of the stress strain curve. So, in the first stage, if you will, as we have already seen, the time molecules or the amorphous regions are the first responders. They are the ones that first respond, and because largely you are deforming disordered regions and you are disrupting secondary forces, they can reversibly align once the load is removed, right? That is the elastic region. Now, you come to the second stage, which is around the necking point, right around yield and the necking point. Now, the lamellae are now oriented such that the chain folds within the lamellae, remember lamellae are the crystalline domains within polymers, and this is the folded chain model that we have seen in lecture 12, and these folded chains are now starting to align. There is a directionality to the loading, and now the folded chains or the chain folds start to align along the loading axis. This happens around necking. Now, if you keep pulling further, you go to the third stage where these blocks of lamellae will now start coming apart, right? And adjacent lamellae within blocks, although they are still connected by time molecules, some of the lamellae have come apart. This happens beyond the yield point. Now, what you start to see is this is related to the idea of plasticity. What you are also seeing here is this reason why you are not able to recover those strains or deformations and make the material go back to its original shape after the yield point is because you are making permanent changes to the network. So, this can occur due to phenomena such as slippage, rupture, sliding, such as shown here, etc. So, all of these things will lead to permanent structural deformations within the or permanent structural changes within the network. If you unload it, it is going to come back along a different path with resulting hysteresis in the sample. Now, in the fourth stage, the blocks of crystalline domains slip past each other at almost constant stress. So, what happens after necking is there is some amount of stress required to pull apart some of these blocks of lamellae, but once you start doing that, then it is fairly easy for them to slip past each other. So, that is why the shape of the curve looks like this in this region, right. Once that initial stress has been achieved to pull apart the different blocks of lamellae, then it is very easy for them to slide past each other. And then if you keep going beyond, you go to the fifth stage where the blocks and time molecules now completely orient along the loading axis. This is the strain hardening region. So, in the fourth stage where you almost get at constant stress, this is what you would call perfect plasticity. These domains slip past each other. If you keep pulling it further, you go to the fifth stage where this is the loading axis. You are pulling the material this way, and you see all the tie molecules and the lamellae have now oriented in that direction. Now these are now going to resist further deformation, that is why you see an increase there, and ultimately a dramatic increase in stress is required to rupture and fail the material, because you are again dealing with covalent bonds. So we started with secondary interactions and secondary forces here in the elastic regime which are recoverable, to ultimately breaking covalent bonds which leads to permanent breakage and failure. That is why you see a dramatic increase in stress in that part of the stress strain curve, leading to eventual failure when these bonds will completely rupture and the material just fails. Again, some of these pictures we have seen earlier in our lectures on crystallinity, lecture number 12, and amorphous nature, lecture number 13. Now in closing, what we will look at, now that we have looked at the different types of mechanical responses, at least under tension, we have looked at how to extract properties from the stress strain curves, and we have also looked at how to understand from microstructural perspective the changes that occur within the material. We will now end with some comments on some mechanical properties of popular polymeric biomaterials that we have already looked at in this course. So the polymers listed here are PTFE, PMMA and PET. And what we are showing here in the table are properties that we have already looked at in this lecture, namely bulk modulus, tensile strength and strain and break. And note the order of magnitude of what we are talking about here. So earlier when I said modulus can be of the order of gigapascals, this is what I was talking about. And of course some sample applications of each of these, namely in vascular grafts, in bone cement or intraocular lens, and in tendon reconstruction. And just to give you a basis or a benchmark for comparison, we are also listing the properties of human ligaments, whose properties are listed here. And the strain at break is not listed as just one value. What we are showing here is, if you are in this region, 8 to 15% kind of strain, you will rupture the ligaments or you will tear them. But if you are within 5 to 8%, you are going to sprain your ligament, with which time can heal. And the normal physiological range for ligaments for strains is about 1 to 4%, right? It is a fairly small number. And all of this can be connected to the collagen present in the ligaments. So that is what leads to some of these properties that we are looking at here. So you see, we are depending on the application, we get very different properties based on the material we are using. And one question to ask here is, why are we not listing these as specific numbers and why are we listing these as ranges? So that is the question that I would suggest that you pause and reflect upon at this point. Why can't we list these as exact numbers? Why are we listing them as ranges? And the reason for that is multifold. I will give you some ways to think about it, and maybe that will give you a good starting point to think about. One is, remember that many of these properties will depend upon molar mass, and we have not specified what the molar mass is here. It will depend upon whether you are testing it under dry or aqueous conditions. It will depend upon whether you are testing it at 37 degrees or at 25 degrees, the effects of which we will see in the next lecture, and it will also depend upon how you have processed them. If you have now processed it into a scaffold with very large porosity, you will get much lower values for many of these things, as opposed to casting a film and testing it under tension. So there are lots of subtleties to keep in mind when you do mechanical testing. That is why standardization is important. We also do not know what the strain rates are, right? So testing conditions also matter. These are all what you would call testing conditions. And of course, intrinsic properties such as molar mass, and properties like that will play a role. You will also have processing affecting the microstructure also, which is also intrinsic, right. So, all of these factors play a role in determining what mechanical properties you get. So, we can only at best provide ranges. Now, in closing, I will leave you with one quick thought about assigning physicality to some of these words that we have seen in this lecture, and then connecting them to some of the properties we have seen. Again, these are words that we use quite often in common parlance, words such as the material is hard, the material is tough, the material is strong, the material is brittle, all of these things, but they all, like I have said in this lecture quite repeatedly, have very specific engineering connotations. So, they must be used very carefully with specific contexts. And shown here are at least 4 ways to think about them. When you talk about a material that is hard and brittle, you are talking about a high elastic modulus, no distinct yield, high tensile strength and low strain at failure. And we have seen that one example of that is PMMA. You can also have hard and strong, where you can have high elastic modulus, high yield, high tensile strength and moderate strain at break. So, these are what, if you have these kinds of features on a stress strain curve, that material could possibly be classified as a hard and strong material. Now, you can also have soft and weak materials with low modulus, low yield, low tensile strength and low to moderate strain at break. And of course, you can have soft and tough, which is low elastic modulus, low yield, moderate tensile strength and very high strain at break, like we have seen for many of the elastomers. So, with that we will close this lecture, and in the next lecture we will take up more specific details of the testing methods, particularly tensile testing, and we will look at the effects of the processing conditions that lead to differences, and also the effect of the testing conditions, where testing wet versus dry, testing at 25 versus 37, testing in relation to the glass transition temperature of the polymer, all of these things we will look at in the next lecture, along with some comments on other modes of testing as well.